Welcome. There is nothing to do now but rest. Let your shoulders sink into whatever is holding you, and let your breath find its own slow rhythm. Nothing here needs your effort. Tonight, we drift through the deep story of time itself, from this quiet room out toward the farthest future of everything. You can simply listen and let sleep arrive whenever it wishes. The universe is currently 13.8 billion years old. That number is almost too large to feel, so let it simply rest in the mind like a held note. Every atom in your body took part in a story that long. The light from the oldest galaxies has been traveling since before Earth even existed. And still, after all that time, the universe continues quietly unfolding. The universe is expanding, and that expansion is getting faster with time. Space itself stretches outward, carrying galaxies apart, like dots on a slowly inflating balloon. This was not expected. For decades, physicists assumed gravity would eventually slow everything down. Instead, distant galaxies are pulling away from us more quickly with each passing age, as though the fabric of space were gently loosening its grip. Dark energy makes up about 68% of the universe's total energy. No one yet knows precisely what it is. It cannot be seen, touched, or held in any laboratory, yet its fingerprints are everywhere in the way galaxies drift apart. Ordinary matter, the stars and planets and dust we can see, is only a small fraction of what fills the cosmos. The rest remains a soft, patient mystery. The cosmic microwave background is the afterglow of the Big Bang. It fills the entire sky, in every direction, as a faint whisper of ancient heat. This light has been traveling for nearly the whole age of the universe. It cooled long ago into the microwave range, invisible to our eyes but detectable by patient instruments. In a very real sense, this glow is the oldest light there is. The sun is roughly halfway through its main sequence lifetime. It has been shining steadily for about 4.6 billion years, and it has about the same span ahead of it. Deep in its core, hydrogen quietly fuses into helium, releasing the light that warms our days. There is no urgency in this process. The sun simply continues, unhurried, exactly as it has for ages. The Milky Way and Andromeda galaxies are on a collision course. They are drawing closer together across a span of millions of light years, pulled by mutual gravity. This meeting will unfold over billions of years, far too slow for any single lifetime to notice. When it happens, it will not be a violent crash, but a long, graceful merging of stars and gas and light. Star formation in the universe peaked about 10 billion years ago. In that distant era, gas clouds collapsed into new stars far more often than they do now. The cosmos was, in a sense, in its most fertile season. Since then, the pace has been gently slowing as galaxies use up the raw material needed to build new suns. We live in a quieter chapter than that early, brighter time. The observable universe contains roughly 2 trillion galaxies. Each one holds billions of stars, and many of those stars likely hold planets of their own. It is a number that dissolves the ordinary sense of scale. The light reaching your eyes tonight, if you looked upward, left some of these galaxies before our earliest ancestors ever walked the Earth. And still, this is only the portion we can see. The rate of new star formation has been declining for billions of years. Galaxies that once burned bright with newborn stars now cool into quieter, more settled places. This is not a sudden change but a long fading, like a fire slowly consuming its last logs. Fewer and fewer new stars are born with each passing age. The universe is, very gradually, growing dimmer. Let your breath find its own rhythm now, without any help from you. Notice the exhale growing a little longer each time, unhurried, like a tide drawing back from the shore. There is no pace to keep, no count to follow, Just the quiet rise and fall, over and over, carrying you a little further from the day. 5 billion years from now, the sun will swell into a red giant. Its outer layers will expand outward, engulfing the space where Mercury and Venus once orbited. It will glow a deep orange red, far larger and cooler than the star we know tonight. This transformation will unfold across millions of years, patient and inevitable. Earth, drifting near that swollen star, will likely be engulfed entirely. Its oceans will have boiled away long before, and its surface will have turned to molten rock. Whatever remains of our world will be drawn into the sun's outer atmosphere. It is a distant ending, far beyond any human concern of today. After its outer layers drift away into space, the sun will settle into a small, dense white dwarf. It will be roughly the size of Earth, yet carry nearly the mass of the sun itself. No more fusion will occur within it. It will simply glow faintly, cooling for ages, a quiet ember of what once was. Red dwarf stars, smaller and cooler than the sun, can burn for trillions of years. They fuse their hydrogen so slowly and steadily that their lives stretch far beyond anything our star will experience. Some of the smallest red dwarfs alive today may still be shining long after every sun-like star has faded. They are the universe's slowest burning candles. Andromeda and the Milky Way, once they meet, will merge into a single galaxy astronomers call Milkomeda. Their spiral arms will stretch and tangle together across hundreds of thousands of light-years. New patterns of stars will form from the encounter. Unlike anything either galaxy holds now, it will be a slow reshaping, not a sudden event. Collisions between individual stars are rare, even in galaxy mergers. The space between stars is so vast that two galaxies can pass through each other with almost nothing touching directly. Gravity reshapes their paths, pulling stars into new orbits rather than crashing them together. What changes is the shape of the galaxies, not the stars within them. Over time, the merged galaxies of the local group will settle into one giant elliptical galaxy. Its shape will be smooth and rounded, without the spiraling arms we see tonight. Star formation within it will slow further, and its light will take on a soft, uniform glow. It will stand alone in the darkness that surrounds it. Beyond the local group, galaxies are already receding faster than light can ever cross the space between us. This does not break any law of physics, since space itself is stretching, carrying galaxies along with it. Those distant lights are moving away at a pace that no signal, however fast, could ever catch. Distance itself is quietly growing. In about 100 billion years, every galaxy beyond our own will slip beyond view. Their light will no longer be able to reach us, swallowed by the ever-widening gap of expanding space. The night sky, whatever remains of it, will hold only the stars of our own merged galaxy. The rest of the universe will simply become unreachable. What astronomers can observe will, in time, shrink down to the light of a single galaxy's worth of stars. Everything beyond that edge will have drifted past the reach of any possible signal. Rexbran, Milkomeda, the merged home of our stars, will become the entire visible universe. Beyond its border, there will be nothing but unbroken dark. The night sky, once crowded with countless galaxies, will hold only the stars we already share. Let your body grow heavy now, the way sand settles at the bottom of still water. Feel your shoulders sink a little further into the mattress, released from carrying anything at all. Let that heaviness move down through your arms, your hands, your fingertips, until they rest without effort. Your legs grow full and warm, pressing gently into the bed beneath them. There is nowhere lighter to be than exactly here, held by this weight, sinking a little more with every breath. 100 trillion years from now, star formation will have ceased across the universe entirely. The last clouds of hydrogen gas, dense enough to collapse into new stars, will have been used up. No new light will ignite anywhere, in any galaxy, ever again. Existing stars will keep burning for a while longer, but nothing new will join them. The universe will still shine, but its shine will be borrowed from the past. This long span of star-filled time carries a name, the Stelliferous Era. It began soon after the Big Bang, when the first stars ignited from primordial gas. It will end when the last stellar nursery finally falls silent. Everything we know as a galaxy full of light belongs to this single chapter. What follows will be far longer and far dimmer. After the last star fades, the universe enters what astronomers call the degenerate era. Ordinary starlight will have vanished, leaving behind only the collapsed remains of stars that once burned. White dwarfs, neutron stars, and black holes will dominate this landscape instead. No fusion will light the darkness from within. What glow remains will come only from remnants cooling toward stillness. Quadrillions of years will pass before white dwarfs finish cooling into black dwarfs. Each one will lose its residual heat gradually, fading from a soft glow to complete darkness. Once fully cooled, a black dwarf will emit no visible light at all. It will simply exist, a cold sphere of matter drifting through an increasingly empty universe. No telescope built by any civilization could ever hope to see one directly. Neutron stars, the collapsed cores of massive dying suns, will remain as dense remnants for eons. Packed with matter so tight that a spoonful would outweigh a mountain, they will hold their shape long after their light has faded. Some will spin for ages, sweeping beams of radiation across the dark. Others will cool into faint, motionless embers. Either way, their density will outlast almost everything else in the cosmos. Brown dwarfs, too small to ever ignite true stellar fusion, may still fuse deuterium slowly across trillions of years. Their glow will be dim from the start, barely warmer than the space around them. Even so, this slow trickle of energy could keep them faintly lit long after brighter stars have gone dark. Astrophysicists consider them among the last embers of the Stelliferous era, fading gradually rather than all at once. Free-floating planets, torn loose from their stellar systems, will drift alone through the darkness with no sun to orbit. Gravitational encounters between stars, rare as they are, can nudge a planet just enough to send it wandering forever. Without a star's warmth, these worlds will cool completely, their surfaces locked in permanent frost. Untethered and silent, they will travel the space between the last remaining lights of the universe. Across almost unimaginable stretches of time, stellar remnants will continue to drift, occasionally passing near one another and colliding. Two burnt-out stars might merge after a slow gravitational dance lasting longer than the current age of the universe. Such collisions will be rare, separated by spans of time too vast to compare with anything familiar. When they happen, they will briefly light the darkness before fading once more into stillness. Protons, the building blocks of atomic nuclei, may not be perfectly stable. Certain theories in particle physics predict that protons could decay, breaking apart into lighter particles. If this happens at all, it would happen on timescales beyond 10 to the power of 34 years. No decay has ever been observed in any experiment so far. The number itself dwarfs every other span of time already described. Should protons truly decay, matter as we understand, it would come apart at its foundation. Atoms would lose their nuclei, and the structures built from them would unravel into lighter particles and radiation. Rocks, remnants, even the darkened embers of dead stars would eventually dissolve. This would not happen suddenly, but as a slow erosion spread across inconceivable stretches of time. Nothing solid would remain to mark where matter once stood. Somewhere far off, a low hum rises and fades, like wind finding its way through an old house. It arrives without warning and leaves the same way, asking nothing of you. Listen to it the way you might listen to rain on a roof, present but undemanding. Let your shoulders sink a little further into whatever is holding you. The hum will return and recede again, and you don't need to follow it anywhere. Long after ordinary stars have gone dark, black dwarfs may not be entirely finished. Under extreme cold and pressure, rare nuclear reactions called cold fusion could still occur within them. These reactions would happen far too slowly to produce any noticeable light or warmth. Even so, across enough time, they could subtly change the composition of these frozen remnants. It would be a transformation without spectacle, unfolding in near total silence. Deep within these frozen remnants, an extraordinary process may eventually take hold. Through quantum tunneling, lighter atomic nuclei could gradually fuse into iron, transforming black dwarfs into what physicists call iron stars. This shift would require a span of time reaching 10 to the power of 1,500 years. Such a number has no true comparison in ordinary experience. It exists purely as a marker for how patient the universe can be. Iron stars, once formed, would not remain stable forever. Their own gravity would eventually overcome the fragile balance holding them together. Depending on their mass, they would collapse either into black holes or into ultra-dense neutron stars. This collapse would mark one of the final transformations available to ordinary matter. After it, almost nothing recognizable as a star would remain anywhere in the universe. With stars, remnants, and even iron stars gone, black holes would come to dominate the mass of the universe. This period is sometimes called the black hole era. Scattered across immense distances, these silent objects would hold what little structure remained. Their gravity, invisible and absolute, would be the last organizing force in an otherwise empty cosmos. Nothing bright would exist to compete with their presence. Even black holes, thought to be eternal, are expected to fade. Physicist Stephen Hawking proposed that they slowly emit radiation, now known as Hawking radiation. Through this process, a black hole gradually loses mass and energy over time. The effect is astonishingly weak, imperceptible on any human scale. Yet, across enough time, it would be enough to unmake even the densest object in existence. Black holes formed from the collapse of ordinary stars are called stellar mass black holes. According to current theory, these would take about 10 to the power of 67 years to evaporate completely through Hawking radiation. Long before that point, everything else in the universe would already have faded into darkness. Their evaporation would be one of the last events with any structure at all. Even then, the process would unfold in near-perfect silence. Far larger black holes, the supermassive kind found at galactic centers, would take much longer to disappear. Some estimates suggest up to 10 to the power of 100 years before they fully evaporate. This number is so vast that it exceeds any timescale already mentioned by an extraordinary margin. When these giants finally dissolve, they would take with them the last substantial structures the universe ever held. After that, only faint radiation would remain. Through Hawking radiation, a black hole loses mass until nothing remains of it at all. The process starts almost imperceptibly, a trickle of energy escaping past the edge of the event horizon. Across immense stretches of time, that trickle removes everything the black hole once held. What began as one of the densest objects ever formed ends as a thinning whisper of radiation, and then as nothing at all. As a black hole loses mass, its Hawking radiation grows hotter, and it radiates energy faster still. This creates a runaway effect: smaller mass, higher temperature, quicker loss, again and again. Near the very end, the process accelerates dramatically, the last fragment releasing its remaining energy in a brief, brilliant burst. Then darkness returns, undisturbed. After the last black hole dissolves, the universe passes into what cosmologists call the dark era. No stars, no remnants, no black holes remain to hold shape or light. Only a thin field of particles drifts through endless distances, spread so widely that structure itself becomes almost meaningless. The universe, for the first time, holds nothing solid at all. Let warmth begin somewhere small, perhaps the center of your chest, a low, steady glow. Let it spread outward now, unhurried, reaching your shoulders, loosening what they carry. Let it move down through your arms, into your hands, until your fingers feel heavy and warm. Let it settle into your legs, your feet, until your whole body rests inside this warmth, held, unbothered, ready for sleep. In the dark era, only a handful of particles remain adrift across the cosmos. Photons carry the last light. Neutrinos pass through everything, almost never interacting. Electrons and their antimatter counterparts, positrons, linger too, scattered so thinly that encounters between them become exceedingly rare. This is the sparse inheritance left behind after every star, remnant, and black hole has gone. Over spans of time longer than any before them, electron-positron pairs may meet and annihilate, turning the last scraps of matter into photons. Each such event releases a small burst of light into a cosmos already mostly dark. These encounters grow rarer as distances between particles stretch ever wider. Eventually, matter itself may thin toward nothing, leaving light as the universe's final substance. Entropy, the measure of disorder within a system, climbs without pause as the universe unfolds. Every star that burns, every particle that decays, adds to this steady accumulation. Energy disperses, structures fade, and order gives way to a more even, scattered arrangement. This tendency, observed everywhere in nature, shapes the story of the cosmos from its beginning to its most distant future. Heat death describes a state in which entropy reaches its highest possible value, and no usable energy remains anywhere. Every temperature difference has vanished, every gradient has leveled out. Without gradients, no work can be performed, no motion sustained, no process driven forward. It is less an ending in the dramatic sense than a final, unbroken evenness spreading across everything that exists. In heat death, temperature differences across the universe approach zero across every corner. Matter and radiation settle into the same faint, uniform chill, indistinguishable from one point to the next. Without warmer or cooler regions, nothing can flow, nothing can change. The universe becomes a vast, featureless expanse, its variations smoothed away by unfathomable time. Heat death does not necessarily mean the universe stops expanding. Space may continue to stretch outward long after all energy differences have vanished. Expansion and thermodynamic stillness are separate ideas. One concerns geometry, the other concerns disorder. A universe could keep growing indefinitely even as it settles ever deeper into uniform, changeless stillness. Physicists have long imagined more than one way the universe might end. Heat death, with its long drift toward stillness, is only one candidate among several. Other proposed fates involve tearing, collapsing, or vanishing outright. Cosmology holds these possibilities side by side, each resting on different assumptions about dark energy and the shape of spacetime. No single outcome has yet been confirmed, beyond doubt. The Big Rip describes a universe torn apart by runaway dark energy. In this scenario, expansion accelerates without limit, stretching space faster and faster. Galaxies would separate first, then stars, then planets, and finally atoms themselves would be pulled apart. Spacetime itself would unravel at its finest seams. It remains a mathematical possibility rather than a settled prediction. Gravity could someday reverse cosmic expansion entirely, according to the Big Crunch scenario. Instead of stretching forever, the universe would slow, halt, and reverse. Galaxies would draw closer together, temperatures would climb, and matter would collapse toward a single dense point. Current measurements of accelerating expansion make this outcome seem unlikely. Even so, it remains part of the wider map of cosmic possibilities. Vacuum decay describes a sudden, catastrophic end, triggered by an unstable quantum field. If the universe rests in a false vacuum rather than its lowest energy state, a bubble of true vacuum could form somewhere in space. That bubble would expand outward at nearly the speed of light, rewriting the laws of physics as it passed. Such an event, if it happened, would leave no warning beforehand. Somewhere in a quiet room, a single ember rests in the hearth, its orange glow low against the dark. It does not need to brighten again tonight. Heat spreads outward in unhurried waves, asking nothing, holding nothing back. Let your breathing match that dimming glow, each exhale a little longer, a little looser, like ash settling into stillness. Rest inside that fading light, and let sleep gather around you. A false vacuum holds energy the way a ball rests on a raised ledge rather than at the bottom of a valley. It looks stable, yet it is not the lowest possible state. If it collapses into the true vacuum below, the energy released would ripple outward as a wall of transformation. Physicists describe this release as effectively unstoppable once it begins, spreading at the fastest speed nature allows. Rudolf Clausius and William Thomson, later known as Lord Kelvin, gave the second law of thermodynamics its modern form in the 1800s. Working independently, both concluded that heat flows from warmer bodies to cooler ones, never spontaneously the reverse. Their insight, born from studying steam engines, eventually reshaped humanity's understanding of the entire universe. A law meant to describe machinery came to describe the fate of everything. Disorder's steady climb lies at the very center of why heat death is thought inevitable. Every physical process, from a star's burning to a cup of tea losing its heat, moves toward greater disorder rather than less. This direction has never been observed to reverse on its own. Multiplied across trillions of years and countless events, that one-way tendency eventually erases every distinction the universe once held. Some physicists argue the universe may never truly reach its highest possible entropy. In an ever-expanding cosmos, the maximum possible disorder keeps rising too, since expanding space allows for more configurations than before. If the ceiling keeps lifting, the universe might approach heat death without ever quite touching it. The finish line, in this view, could recede exactly as fast as anything nears it. The Poincaré recurrence theorem suggests that, given enough time, a system may return arbitrarily close to a previous state. Applied to the cosmos, this raises a strange possibility. Random fluctuations in an equilibrium universe could, however rarely, reassemble pockets of order. Such events would require timescales so enormous they dwarf comparison to anything in ordinary experience. A momentary structure could flicker into being only to dissolve back into the surrounding evenness. Random fluctuations, in principle, could briefly assemble something resembling a conscious mind. Physicists call these hypothetical entities Boltzmann brains, named after the same physicist whose work on entropy shaped this whole story. Such a mind would appear complete with memories and thoughts, yet arise from nothing but chance rearrangement of particles. It would flicker into being for a moment, then dissolve back into the surrounding stillness. Cosmology finds itself confronted by an unsettling puzzle these hypothetical brains present. If given enough time, random fluctuations should produce far more Boltzmann brains than ordinary observers like us. This raises a strange question about why our own orderly universe exists at all, rather than a scattering of momentary minds. The puzzle remains genuinely unresolved among those who study the shape of the cosmos. Freeman Dyson, a physicist working in the 1970s, imagined how civilizations might endure into the unimaginably distant future. He wondered whether intelligence itself could outlast the stars, adapting as the universe grew colder and emptier. Dyson approached the far future not with despair, but with careful calculation and quiet curiosity. His papers on the subject remain foundational to this entire field of speculation. His idea, later called eternal intelligence, proposed that a civilization could slow every thought to conserve dwindling energy. As the universe cools, less energy remains available for computation of any kind. By stretching each thought across longer intervals of time, Dyson suggested that mental activity could, in theory, continue indefinitely. Thought itself would simply unfold at an ever more unhurried pace. A civilization could, in theory, rest through the coldest stretches of cosmic time to save energy for later use. Rather than thinking continuously, it might store reserves and remain dormant for eons at a stretch. When enough energy had accumulated, it could briefly awaken to think, compute, or simply reflect. Long dormancy, brief awareness, repeated across ages beyond ordinary imagining. Let your jaw loosen, the smallest muscles near your ears releasing their hold. Your eyelids grow heavier now, resting fully closed, without effort to keep them that way. Behind them lies a soft darkness, wide and unlit, asking nothing of you. Stay there a while, in that private dark, letting your face settle into stillness. There is only this dim, unhurried space behind closed eyes, and you resting inside it. A Dyson sphere would wrap a star entirely, gathering its light before it ever escapes into open space. Freeman Dyson first described such a structure as a way to capture nearly all of a star's energy output. A civilization surrounding its sun this way would have access to an almost unimaginable power supply. The star's light, once scattered across the galaxy, would instead be caught and put to use. Structures might one day surround a black hole instead of a star, drawing power from its intense gravity. Falling matter releases enormous energy as it spirals inward, energy that could theoretically be gathered rather than lost. Such a structure would need to withstand extreme forces near the black hole's edge. In this way, even the darkest object in the universe might become a source of light. Ripples released when two black holes merge could, in theory, be gathered as an energy source. These gravitational waves carry away enormous amounts of energy as they spread outward through spacetime. Detecting them already required instruments sensitive to the tiniest imaginable distortions. Harvesting them for use would demand technology far beyond anything humanity currently possesses. The Penrose process describes a theoretical way to draw energy from a spinning black hole's rotation. Proposed by physicist Roger Penrose, it relies on the strange region just outside the black hole's edge, where space itself gets dragged along with the spin. An object entering this region and splitting apart could, under the right conditions, escape with more energy than it had before. The black hole, in turn, would slow its spin ever so slightly. Even the slow-fading light of an evaporating black hole could, in theory, be gathered rather than let dissipate. As Hawking radiation escapes near the very end of a black hole's life, its final burst of energy grows unusually intense. Structures built to survive such proximity might collect this last flare before it scatters. It would be a strange kind of harvest, tending an ember at the edge of nothing. Stars themselves might be redesigned to burn more slowly, stretching their usable lives far beyond their natural span. Structured engineering could adjust how a star loses mass, how fast its fuel converts to light, or how its layers mix and churn. Such techniques remain entirely theoretical, sketched only in physics papers rather than blueprints. Still, the idea suggests that even stellar aging is not necessarily fixed. One such idea is called starlifting, a hypothetical method of drawing material away from a star's outer layers. By removing mass before it can be consumed, a civilization might slow the star's rate of fuel use. The lifted material could even be repurposed elsewhere, perhaps to build new structures or seed new worlds. It remains speculative, but it treats a star less as a fixed object and more as a resource to manage. Because cosmic expansion is not perfectly even everywhere, some regions stretch apart more gently than others. Advanced civilizations, in principle, might drift toward these calmer regions to delay isolation. Denser areas of the universe resist the pull of expansion more effectively than sparse, empty stretches. Moving toward such places would not stop the universe's growth, but it might soften its consequences for a little longer. Galaxy clusters, bound tightly by gravity, resist the stretching of space more than the emptiness between them. Migrating toward such clusters has been proposed as a way to delay the slow drift into cosmic solitude. Within a bound cluster, galaxies remain close enough that light and gravity can still connect them. Outside it, the widening dark eventually cuts every connection away. A galaxy still in the process of forming holds more raw material for future stars than an older, spent one. Traveling toward such a galaxy, some have proposed, could theoretically extend a civilization's access to fresh starlight. Young galaxies are rich with gas clouds, still collapsing into new suns. Reaching one would mean trading a fading neighborhood for a still blooming one. Notice how your breath has already begun to slow, each inhale a little shorter than the exhale that follows it. There is no need to change anything about it, only to notice the rhythm as it is. Let the air leave your body a little further each time, further than seems necessary, further than feels urgent. With each release, let your shoulders sink a fraction more into whatever is holding you. There is only this breath, and then the next one after it. Beyond a certain point in cosmic time, only structures bound tightly by gravity are expected to endure. Galaxy clusters, held together by their own mass, resist being pulled apart by expansion. Everything not gravitationally bound will eventually drift beyond reach, swallowed by the widening dark between things. What remains would be a scattering of isolated islands, each cluster alone in its own pocket of space. There is a limit to how far into the universe anyone could ever travel, no matter how much time passes. This cosmological horizon marks the edge beyond which space is expanding too quickly for light or anything else to cross. Everything beyond that edge becomes permanently unreachable, not because of distance alone, but because the space itself keeps growing faster than it can be crossed. It quietly draws the boundary of what will ever be possible to explore. To make the most of a shrinking energy supply, some physicists propose converting matter itself into computronium, matter arranged purely for computation. Every particle would be organized not to shine or burn, but to think, calculate, and preserve information as efficiently as possible. In a universe running low on usable energy, computation per unit of energy would become the measure that matters most. It is less a machine than a civilization rebuilt entirely as thought. Computronium describes a hypothetical form of matter arranged so that every atom, every spin, every possible degree of freedom serves one purpose: processing information. It would not shine like a star or radiate like a furnace. Instead, its structure would be tuned entirely toward calculation, memory, and the careful shaping of thought. Physicists imagine it as the far end of efficiency, matter reorganized until no part of it remains wasted. In 1961, a physicist named Rolf Landauer showed that erasing a single bit of information carries an unavoidable energy cost, however small. This cost depends only on temperature, tracing a direct line between information and thermodynamics. Any computation that forgets what it once knew must release a little heat into its surroundings. Landauer's principle would matter deeply to any far-future mind trying to think for as long as possible on as little energy as possible. Cooling a computational system toward absolute zero could shrink the energy price of every operation it performs. Colder substrates suffer less thermal noise, allowing information to be processed with greater precision and less wasted motion. Future minds built from computronium might drift through the coldest reaches of a fading universe by choice, not misfortune. In such cold, a single calculation could stretch further, sipping only the faintest trace of energy to continue. Reversible computing imagines a kind of calculation that never truly forgets, undoing each step as easily as performing it. Because no information is erased, Landauer's limit no longer applies in the same way, and energy loss could approach a vanishing minimum. Such logic would not run in one direction only. It could fold back upon itself without cost. A mind built this way might compute for immense stretches of time, while spending almost no energy at all. Quantum computing might allow information to be processed using superpositions and entangled states rather than the simple switches of ordinary machines. Certain quantum operations could, in principle, approach the same low thermodynamic cost as reversible computing. Whether this advantage would survive the extreme cold and sparse energy of a far future universe remains an open question. Even so, it offers another thread of hope for minds seeking to think longer on less. A more radical proposal imagines transferring a mind entirely into a computational substrate built from computronium. Thought, memory, and identity would be re-expressed as patterns of information rather than the biology that first gave rise to them. Freed from a body's fragile chemistry, such a mind might be run more efficiently, tuned precisely to whatever energy remains available. Whether consciousness can survive such a transfer is a question philosophy has not settled. Digital minds, once uploaded, could theoretically stretch their own sense of time across a nearly endless span of remaining energy. A single thought might unfold across centuries of outside time while feeling, to the mind having it like only a breath. This kind of patience would let awareness persist long after stars and even black holes have faded. Subjective time, in this picture, becomes something a mind can choose to spend carefully or not at all. Feel the weight of your body now, settling deeper into the surface beneath you. Let your feet grow heavy first, heavier than they have felt all day, sinking as though gravity has doubled just for you. Let that heaviness climb upward, through your legs, into your hips, warm and full through your lower back. Your arms follow next, heavy at the shoulders, heavier still at the fingertips, resting exactly where they land. Even your head, finally, grows heavy against the pillow, with nowhere left to carry it but down. Civilizations navigating a darkening universe might use the gravity of a passing black hole as a slingshot, gaining tremendous speed without spending fuel of their own. A ship diving close to such a mass could borrow momentum from the black hole's motion, flinging itself onward across immense distances. This kind of gravitational assist, already used by spacecraft crossing our own solar system, could in theory be scaled up to interstellar or even intergalactic journeys. It would be movement powered by falling, not burning. Engineers of some distant future might construct artificial black holes deliberately, using immense concentrations of energy to fold matter into a stable, compact form. Such a black hole could act like a battery, storing vast energy within its mass and releasing it later as controlled radiation. Lowering its mass would raise its temperature, letting a civilization tune exactly how much energy escapes and when. It is a strange kind of vessel, one that stores power inside the very darkness that swallows light. Micro-black holes, if they could be made small enough, would radiate away their mass quickly through Hawking radiation, releasing energy in a steady, controllable stream. A civilization might position such a tiny black hole within a containment field, catching every particle it emits before that energy escapes uselessly outward. It would function like a miniature furnace, small enough to hold, bright enough to sustain a colony for a very long while. The darkness itself would become the fuel. Freeman Dyson once calculated that a fixed, finite amount of energy could still support an infinite number of thoughts, provided each thought used less energy than the one before it. By slowing computation and cooling its processes gradually, a mind could stretch a limited resource across unlimited time. Dyson's arithmetic suggested that consciousness, structured wisely, need not be bound by scarcity alone. Careful pacing in his equations mattered more than raw supply. Certain cosmological models suggest that as space keeps expanding, even radio signals between surviving pockets of civilization could eventually fail to arrive. Distances would grow faster than any message could cross them, stretching light itself then until it faded below detection. Two groups, once neighbors across a galaxy, might drift into total silence without any dramatic event marking the moment. The universe would simply grow too wide for words to survive the journey. Communities separated by the widening gaps of space could become permanently cut off from one another, each carrying on in isolation. No collision, no conflict would cause this separation, only the quiet stretching of the space between them. Over enough time, each surviving group might come to believe it was entirely alone in the universe. Isolation, in this future, would arrive not as an event, but as a slow and total drift. A quieter kind of proposal imagines slipping through a wormhole, a theoretical bridge folding two distant points of space-time together, as a way of stepping outside a dying universe altogether. Rather than outlasting entropy, a civilization might simply leave through a passage in the fabric of space itself. Such a bridge would need to remain open long enough and stable enough for something to pass through unharmed. It is an idea built from mathematics that permits it, without proof that nature allows it. Wormholes exist today only within the equations of general relativity, described in careful detail yet never observed by any telescope or instrument. Physics permits their geometry on paper, curved tunnels connecting distant points of spacetime, but nothing confirms that such structures could ever form or endure in nature. They remain elegant possibilities, waiting quietly at the edge of what mathematics allows and what the universe actually contains. For a wormhole to stay open long enough for anything to pass through it, physicists have proposed it would need something called exotic matter, a substance with negative energy density. Ordinary matter tends to pull space inward, collapsing such a passage before it could ever be used. Negative energy, strange as it sounds, would push outward instead, holding the throat of the wormhole stable. No one has ever gathered enough of this substance to test the idea directly. Curiously, physicists working with light itself have found something resembling negative energy in a laboratory setting. Squeezed vacuum states, carefully engineered arrangements of quantum light, exhibit brief regions where energy density measures below what empty space would normally allow. It is a small, fleeting effect, nothing like what a wormhole would require, yet it hints that negative energy is not purely theoretical. Nature, in tiny measured moments, already permits a glimpse of it. Somewhere outside your window, a low hum may be settling into the walls, the kind of sound a house makes when everything else has gone still. It rises for a moment, then fades, the way distant traffic rises and fades, or wind moving through unseen trees. You do not need to listen for it. Let it arrive if it arrives, and let it go if it goes, your breath following its own unhurried rhythm beneath it, needing nothing from you but to keep on breathing. Between two ordinary metal plates, held impossibly close in a vacuum, physicists have measured something called the Casimir effect, a tiny but real negative energy density. The plates draw toward each other, pulled by fewer quantum fluctuations existing in the narrow gap between them than in the open space around them. It is a small, quiet experiment, easily overlooked, yet it stands as solid proof that negative energy is not only mathematics. It exists, faintly, right here in a laboratory on Earth. Inside certain black holes, according to a handful of theoretical models, an entirely new universe might come into being. As matter collapses beyond the event horizon, the mathematics describing that collapse resembles, in some formulations, the birth of an expanding cosmos. This newborn universe would not be visible from outside. It would exist beyond reach, folded into its own separate expansion. The idea remains explored only on paper, tested through equations rather than observation. Baby universes, according to this class of theory, might bud away from our own like small offshoots along a grapevine. Each budding universe would carry its own expanding space-time, sealed the moment it forms. No signal, no light, no trace would pass between parent and child. The image is almost biological, a cosmos capable of reproducing itself across scales too vast to picture. It remains a mathematical possibility rather than a measured fact. Lee Smolin, a theoretical physicist, once proposed that universes might evolve much as living things do. In his idea, called cosmological natural selection, universes that produce many black holes would tend to produce many offspring universes, each inheriting slightly altered constants. Over vast cycles, this process could favor universes especially good at making black holes through this analog of selection. It remains speculative, elegant, largely set aside by mainstream cosmology today. Creating a baby universe, if such a thing were possible, might offer a strange kind of escape route. Matter or information falling into a black hole, ordinarily thought lost, could in principle pass into this newborn spacetime rather than vanishing entirely. Nothing would return to tell of it. The transfer would be one way, sealed the instant it happened. The notion offers a curious answer to an old puzzle about where things go when a black hole consumes them. A handful of physicists have speculated about deliberately engineering a universe with constants unlike our own. In thought experiments, adjusting the strength of gravity or the mass of certain particles might yield a cosmos capable of forming stars, chemistry, perhaps life, under entirely different rules. Building such a thing would require compressing enormous energy into an impossibly small volume. The exercise stays theoretical, a way of testing how flexible the laws of physics truly are. Nucleating a pocket universe, according to inflationary theory, might require energy density concentrated within an extremely small region. The physics resembles the same process thought to have inflated our own universe from an infinitesimal seed. Achieving such density would demand compressing energy far beyond anything matter on Earth could withstand. Even so, the equations describing inflation do not forbid it happening again, elsewhere, on scales too small to notice. The energy required to create even a modest new universe would likely dwarf anything a civilization could ever gather. Estimates run far beyond the total output of every star combined across the observable cosmos. Harnessing such energy would mean commanding forces closer to the Big Bang itself than to any engineering project imaginable. For now, the numbers alone place this idea outside practical reach, however sound the underlying mathematics might be. Multiverse theories describe our universe as a single instance within a far larger ensemble, each region governed by its own laws and heading toward its own ending. Some might expand forever into cold stillness. Others might collapse, or tear, or fade, in ways quite different from ours. If true, heat death would be a local story, not a universal one, unfolding here while other regions follow entirely separate paths. Eternal inflation theory suggests that new universes are being created endlessly, bubbling into existence within an ever-inflating background that never stops expanding. Each bubble grows into its own separate cosmos, disconnected from the others by distances that will never be crossed. Our own universe in this picture is one such bubble among a number too large to state meaningfully. The process, if real, has no beginning we can trace and no foreseeable end. There is no need to do anything now but let warmth gather, low and slow, somewhere behind your eyes. Let it settle there first, a small private heat spreading down through your forehead, unclenching whatever held tight through the day. From there it moves into your jaw, your shoulders, loosening what has been carried too long. It continues into your chest, your arms, your hands resting wherever they rest. Warmth pools in your hips, your knees, the backs of your legs, sinking all the way to your feet until your whole body rests inside it, heavy and warm. If the multiverse turns out to be real, then heat death may not be a universal sentence at all. Other regions, governed by different physical constants, could be young where ours is old, or expanding where ours has gone still. A colder, emptier fate here might simply be the local weather of one bubble among countless others. Elsewhere, under different laws, something resembling vitality could persist far past the point our own universe grows dark. Certain cyclic models propose that our universe's ending is not truly an ending, but a threshold. As expansion stretches everything toward stillness, some versions of these models imagine density and energy folding back inward, collapsing toward a singular point. From that point, a new Big Bang could emerge, spilling outward into a fresh universe with fresh laws. Death and birth, in this picture, are simply two names for the same transition. Conformal cyclic cosmology, developed by the physicist Roger Penrose, proposes something stranger still. In this framework, the featureless, stretched-out emptiness of heat death becomes mathematically indistinguishable from the smooth, uniform state just after the Big Bang. Scale itself, Penrose argues, stops mattering at those extremes. What looks like an ending, seen the right way, may simply resemble a beginning wearing a different face. Cosmologists generally treat conformal cyclic cosmology as an elegant idea rather than an established fact. No confirmed observation has yet supported the specific signatures the theory predicts, such as faint circular patterns said to be left behind by earlier cosmic cycles in the background radiation. Searches have been made, and debates continue, but the evidence remains thin. The theory endures more as a mathematical possibility than as settled science. Phase transitions in vacuum energy offer another route by which structure might return after everything has gone dark. If the vacuum itself shifts to a lower energy state, the sudden release could, in principle, seed new fields, new particles, even new pockets of matter. Such a transition would ripple outward, transforming a settled emptiness into something briefly alive with possibility again, before dissolving once more into stillness. Structure and information may simply be things the universe cannot hold on to forever. Every pattern, every arrangement of matter into something meaningful requires energy differences to maintain itself. As those differences erode, the fine detail of galaxies, minds, and memories may be unable to survive in any form. What remains, eventually, might be a version of existence with no distinctions left to preserve. A number of physicists argue that infinite computation might still be possible, even in a universe expanding forever. The idea depends on finding ways to perform each calculation using less energy than the one before it, endlessly halving the cost. If such a sequence could continue without limit, A mind built on that process might think an unbounded number of thoughts spread across an eternity of slowing time. Frank Tipler, working in the 1980s, gave this idea a name, the omega point. He proposed that as the universe approached its final collapse, available energy and processing speed could rise without limit, allowing an effectively infinite amount of computation to occur within a finite stretch of remaining time. In his vision, thought itself could become boundless in its last instant, even as the universe closed in around it. Tipler's omega point depends on the universe eventually recollapsing in what is called a big crunch, gravity overcoming expansion and pulling everything back inward. Cosmologists now consider this scenario unlikely, given how strongly the evidence favors continued acceleration rather than collapse. Without a crunch to compress and accelerate computation, the mechanism Tipler imagined loses the stage it was built to perform on. Current evidence favors continued expansion over any eventual return to collapse. Distant supernovae, measured across billions of years, show the universe's growth speeding up rather than slowing down. Every careful survey since has confirmed the same pattern. Barring some undiscovered shift in the nature of dark energy, the universe appears set on an outward path, one that leads toward cold and distance rather than any final gathering back together. Somewhere in the room, one ember settles into ash, its glow fading by degrees, never all at once. Notice how the last light doesn't disappear. It eases, edge by edge, into deeper red, then into shadow. Let your breath find that same unhurried fade. Each thought you are holding can dim like that ember, glowing less and less, needing nothing from you but time passing. Rest here in the last warm color before dark. Harnessing dark energy itself, some propose, could one day power civilizations far outlasting any star. If the force driving cosmic expansion carries usable energy, a technology tapping directly into that flow might never run dry. Such a civilization would draw power not from burning matter, but from the fabric of space stretching outward. The idea remains untested, resting only on mathematics and hope. Dark energy's nature remains one of the deepest unsolved mysteries in physics. It makes up most of the universe's energy content, yet no experiment has ever captured it directly. Some call it a property of space itself. Others suspect a field yet undiscovered. Whatever it turns out to be, it already shapes the fate of everything that follows. If dark energy weakens over time, the outward rush of galaxies might eventually ease. A weakening force would mean less push against gravity's pull, allowing the universe's growth to gradually taper. Such a change could postpone isolation between galaxies, keeping distant light reachable a little longer. No observation yet confirms this weakening, only its possibility within current equations. Quintessence models, a family of theories in physics, allow dark energy's strength to shift across immense stretches of time. Instead of a fixed constant, these models imagine dark energy as a dynamic field, capable of rising or falling in influence. Such models remain unproven, sitting alongside simpler explanations. Even so, they offer a door through which the universe's fate might not be fixed after all. A shift in dark energy's strength, however slight, could alter every prediction made about the universe's final chapter. Models built on a constant push lead toward endless cold expansion. Models built on a weakening or strengthening force point toward entirely different outcomes, from gradual stillness to sudden tearing. The universe's true ending may hinge on a property we have not yet measured. String theory suggests hidden dimensions, folded impossibly small around every point in space, might one day be tapped for energy transfer. In this framework, gravity leaks between dimensions more freely than light or matter do. If true, a civilization might learn to draw power through those extra folds, reaching resources unseen by ordinary physics. The mathematics allows it, the engineering remains entirely imagined. Escaping into those extra dimensions, some speculate, could offer a way around heat death itself. If matter or information could pass through folded space into another dimension, entropy's slow climb in our own universe might not apply there. Such an exit would require physics far beyond anything demonstrated. Yet the thought experiment reveals how deeply humanity resists a final ending. Brain cosmology proposes that our entire universe exists as a membrane suspended within a larger, higher dimensional space. In this picture, other membranes, other universes, might drift nearby, invisible to us, except through gravity's faint pull. Everything we know, every galaxy, every star, would rest on the surface of that one sheet. It is a vision drawn from mathematics, offered without proof, yet strangely humbling to consider. Colliding brains within this same framework could theoretically ignite an entirely new Big Bang. If two such membranes drifted together across higher dimensional space, the impact might release enough energy to birth a fresh universe, complete with its own laws and history. Some theorists suggest our own universe may have begun this way, one collision among countless others. It remains a speculative idea, resting at the far edge of theoretical physics. Whether escape from heat death is even a meaningful idea is a question philosophers of physics now raise outright. To speak of surviving an ending, they note, assumes survival still means something once time, change, and difference have dissolved. Perhaps the phrase itself borrows a shape from lives lived inside contrast and consequence, a shape that may not carry over. The universe's final state might simply lie outside the vocabulary we use to imagine it. Let your jaw loosen, just slightly, as though it had been holding a word it no longer needs to say. The eyelids grow heavier now, settling like curtains drawn against a low evening light. Behind them, there is only a warm, unlit hush, wide and undemanding. Nothing there is asking to be seen. Let the face rest in that darkness, unwatched, unhurried, entirely its own. Consciousness, information theory suggests, is not free-floating thought, but a physical process, and every physical process needs a gradient to move through. A gradient is simply difference, a warmer place beside a cooler one, a signal beside its absence. Thought rides on such differences the way a stream rides a slope. Where every point equals every other point, there is nothing left for a mind to travel along. Without energy gradients, no computation and no thought could theoretically occur at all. A processor, biological or otherwise, works by letting energy fall from a higher state to a lower one, using that fall to shift a bit, fire a neuron, complete a step, remove every slope and nothing falls. The machinery of thinking, however built, needs somewhere for energy to go. Any form of life, many argue, requires thermodynamic disequilibrium simply to keep existing. A living thing is a small pocket of order maintained by constant exchange, taking in useful energy, releasing the used-up remainder. Stop that exchange, and the pocket collapses into sameness with its surroundings. Life, in this sense, is less a substance than an ongoing conversation with imbalance. Total equilibrium implies that no possible physical process, including thought, could occur within it. Equilibrium is the condition heat death describes, everything the same temperature, everywhere, forever. In such a state, there is no direction for energy to travel, and therefore nothing for change to use. It is less an ending with drama than an ending with none at all, a stillness beyond even quiet. Some scientists consider heat death survival scenarios purely speculative extrapolations, useful for thought but unsupported by evidence. Dyson spheres, digital mines, harvested black holes all remain mathematically possible, none observed, none tested. The distance between what equations allow and what nature permits can be enormous. Holding that distance honestly, rather than closing it with hope, is itself part of doing careful science. Current physics cannot rule out unknown laws altering the universe's ultimate fate, however confidently the calculations run. Every model rests on what is known today, and history has repeatedly shown gaps waiting to be filled. Dark energy alone remains largely mysterious. A future discovery, quiet and unannounced, could still rewrite everything that follows from here. Quantum fluctuations in a true vacuum could theoretically create localized order, even amid apparent nothingness. Empty space, at its smallest scale, is never perfectly still. Pairs of particles flicker briefly into being and vanish again. In principle, a sufficiently rare fluctuation could assemble something ordered, even something resembling structure, out of that restless quiet. The vacuum is emptier than air, yet never fully at rest. Such fluctuations are statistically extraordinarily rare over cosmic timescales, rare in a way ordinary numbers struggle to hold. The odds of anything meaningful assembling this way are vanishingly small, and the waiting time involved would dwarf every era already described. Even so, given enough time, and heat death offers time without end. Even the near impossible is not quite the same as the impossible. Our proposal imagines civilizations releasing self-replicating probes into the dark, carrying compressed records of everything they once knew. Each probe would gather raw material from passing debris, build copies of itself, and send them onward in every direction. Over unimaginable spans, such a swarm could outlast its makers by unthinkable margins. The idea treats memory itself as a seed, scattered wide enough that some fragment might always be germinating somewhere. Von Neumann probes, named for the mathematician who first described self-copying machines, could in theory spread across the cosmos for long-term survival. Each device would replicate using whatever raw material it finds among asteroids or dust, producing descendants that carry forward the original design. Given enough time, a single launch could seed an entire galaxy. The concept turns exploration into propagation, letting machines outlive stars, planets, and perhaps even their creators' memory of why they were sent. Let the breath lead the way now, in through the nose, unhurried, and out through parted lips, a little longer than it came in. Each exhale can carry a little more weight from the shoulders, the jaw, the space behind the eyes. There is no need to count, no need to time it, only to notice the rhythm returning, wave after wave, longer on the way out than on the way in. Let it carry you further down. Encoding information into cosmic rays has been proposed as another way to preserve knowledge across deep time. High-energy particles already cross the universe largely undisturbed, traveling for eons without decay. A civilization might, in principle, imprint patterns onto such streams, letting them carry meaning long after their senders are gone. Whether such a signal could ever be read again by anyone remains entirely unknown. Physical laws, as they are currently understood, do not allow any permanent escape from entropy's slow increase. Every process examined so far, from burning stars to thinking minds, spends order to produce disorder somewhere else. No known mechanism reverses that direction for good. The universe's ledger, as far as physics can read it, only ever balances toward the same quiet decline. A deeper question sits beneath all of this: whether the universe is fully deterministic, its ending fixed the moment it began. If every particle's fate already follows from initial conditions, then heat death is not a possibility, but a certainty already written. If chance plays a real role, some outcomes might remain genuinely open. The debate over escape, in this light, becomes a debate about the nature of physical law itself. One estimate places heat death at a time, written as 10, raised to the power of 10, raised again to the power of 56 years from now, a number that leaves the everyday meaning of counting far behind. Written out in full, the digits would stretch beyond any page, any lifetime, any civilization's patience. It is less a countdown than a horizon so distant that time itself seems to lose its usual shape. The universe's current age, 13.8 billion years, is negligible against timescales like that. Stretched onto a single line representing heat death's arrival, the entire history of stars, galaxies, and every living thing so far would occupy a sliver too small to see. Everything humanity has ever known has happened in what amounts to the universe's first breath. Speculative survival strategies, hibernating mines, harvested black holes, seeded probes remain entirely untestable with current technology. No experiment can simulate trillions of years, and no instrument can observe the far future directly. These ideas live instead in careful mathematics, honest extrapolation, and imagination disciplined by physical law. They are less predictions than exercises in seeing how far reasoning can travel before the ground runs out. The universe's ultimate fate still depends on properties of dark energy that remain unresolved. If its strength stays constant, expansion continues forever toward heat death. If it weakens or strengthens, the story could bend toward a crunch, a rip, or something not yet imagined. The ending, in other words, is still being written by a force no one has yet fully measured. Meaning and identity, many physicists argue, would lose all definition in a state of total heat death. Without gradients, without change, without difference between one moment and the next, the very concepts that give a self its edges may cease to apply. A mind requires contrast to notice anything at all. In perfect sameness, there may be nothing left to distinguish a thought from its absence, or a person from the space around them. Whether anything could outlast such a state touches physics, philosophy, and speculative engineering all at once. Equations describe entropy and energy, but they cannot say what survival would even mean without a self to survive. Philosophers ask whether continuity of thought matters if nothing changes within it. Engineers imagine structures and machines, yet every design still answers to the same thermodynamic limits that shape stars and galaxies alike. No consensus exists on whether such an escape is possible, and perhaps none is needed tonight. The universe will spend unimaginable ages becoming what it becomes, long after every question asked about it has been forgotten and asked again by someone else. For now, there is only this quieter, nearer universe, a bed, a breath, a dark room holding you gently in its own small pocket of time. Rest inside it. Good night.